Okay, part 3 to 3.1. I know it takes a little while to go through these. It's amazing how long it feels. We do a lot of them. We're going to do higher order derivatives on that 3.1 sheet. So f prime, f double prime, f triple prime, the fourth derivative down below. We did these in terms of motion at one point before the break too. We called this like, hey, one of the common things we talk about, this would be like position, velocity. If you take the first derivative, it's the rate of change of position. And then each derivative is the rate of change of whatever you're deriving. So if you do the first derivative, it's the rate of change of position. The second derivative is the rate of change of the rate of change, or the rate of change of velocity. We call that acceleration. The rate of change of velocity is acceleration. The rate of change of acceleration, what the third derivative finds, is the jerk. And then we had some fun in class. You guys didn't believe me. Some of you were skeptical, which is probably safe. But the rate of change of jerk is snap. Okay, and it comes right out of course, good old fashioned, like, we were just watching, what was it? Like, it was Legally Blonde. It came in a funny era and time. It was an outstanding film. I think mildly inappropriate in today's culture, but there's parts of it you just can't help but really love. So that's where the snap reference came in, if you want to look back at that. So f prime of x is 7x to the sixth minus 8x to the third plus 10x minus 3 is the derivative. The derivative of 9 is 0. This is a really good place to just sit back and say, okay, this is the power rule for something simple. I didn't have to simplify it. I didn't have to do it with fractions or negative exponents or radical exponents, that type of stuff. So radical square roots and things like that turned into fractional exponents. This was clean and easy first derivative. The second derivative means take the derivative of the first derivative. So we just keep going. So now it's 42x to the fifth minus 24x to the second, and then that derivative, that should be a 10x, by the way, up top there, and the derivative of 10x should be just 10, okay, and then we took the derivative of the negative 3 in the first derivative, and that would be 0, so it's gone. So every time we took the derivative of a constant, it disappears at 0. And then now the third derivative is the derivative of the second derivative. We apply the power rule to the second derivative. So we're going to get 84x to the fourth, and then minus 48x. Derivative of 10 is 0. And then the fourth derivative would be 4 times 84, 32 plus 6, 320 plus 16. What is that? 336x to the third minus 48. And that's it. That's our 4 derivatives consecutively. They do give us information, so they all speak to the graph of f of x. They tell you if f of x is the position, say a height, or where it is left or right on a horizontal plane. The first derivative tells you how fast it's moving, left and right, up and down. Okay, gives you velocity, and it does give you direction. Positive would be up or to the right, and negative would be left or down, usually. It's whatever somebody assigns to it, really. And acceleration is how fast the velocity is changing. Speeding up or slowing down is related to that. Jerk is a change of acceleration, and snap is getting down to particle physics when you start talking about that, so maybe we'll leave that be. But the deal is each derivative tells you a different characteristic of f of x, and that's what the multiple derivatives are all about, the full story of what's going on in f of x. So now let's move on to the next one. Here's a little algebra back to having, before we take on this problem, you want to rewrite this. So it'd be x to the half, and x to the negative 2 is in good shape. You know, it could have been 1 over x squared, could have been written there, and we'd have to fix it, but it's already set for us. We've got the negative. So now when we derive this, the derivative of x to the 1 half is 1 half x to the negative 1 half, because 1 half minus 1 is negative a half. And then the derivative of x to the negative 2 is negative 2x to the negative 3. Now, if we want to keep going to the second derivative, I shouldn't simplify this because this is already in that lovely power rule form, number times x to a power. So leave it, and we'll just keep going. So negative a half times a half is negative a fourth, the second derivative, and that's what this stands for. This notation means derive again. I'll show you where that notation comes from here in a moment. And that would be x to the negative 3 halves, because you're subtracting 1 from it. And then negative 3 times negative 2 is 6x to the negative 4. So that's your second derivative, which would tell you acceleration if this were about motion. The derivation of that funny notation, it actually is the derivative of dy dx And if you kind of distribute it, there is a little bit of mushiness in here. There's actually parentheses around this. But if you distribute the d, dy in there, d times d is d squared, and the dx times dx is dx squared. So you're taking the derivative of dy dx, and there is where that notation comes from. Okay, so we did some multiple derivatives to get more information about our graph. The derivative on your calculator, so it does this. I don't have a screen to show you the calculator at the moment, and I keep trying to get hold of that, but with this whole shutting down the schools thing, I don't have access to all my tools, and I can't get them as I'm on the school's power system. So what I'm going to do instead is I'm going to pull up just some kind of graphing calculator demo or anything like that, and I'm going to get these values. So when you want to just get the slope of the tangent line at these specific x values, which is what's happening, this is just, hey, find the slope of the tangent line to the given function at these x values. Please go get that slope for me, please. Then don't mess around. Just go find some way. There you see me uploading videos. But if I grab my favorite demo or a graphing calculator, anything you want, and I start, then this will do the job. So I'm going to put my f of x in there. So the first one is, and even using this notation is kind of fun. So 1/2 and x, and then you write squirt, and 2x minus 1. Done. And then down below, if I want to know, hey, what's the slope of the tangent line at x equals 4 to this weird looking radical graph? And you just write f prime of 4, and it'll give you, oops, of course I didn't hit f prime. That's the second derivative. So f prime of 4 comes right there. And so you can also do f of 4, but this is where I think you'll notice sometimes on the last test, there are different things. F of 4 means the y value at a given spot at x equals 4. F prime of 4 means the slope of the tangent line at x equals 4. Two different things. So if I go back, I can write 2.078, and it says, I think it says round to a certain number of decimal places. Probably should go to 3 decimal places, so I'll do that right now. That'd be 2.079. Let me go back to my sheet. 2.079. And again, I will find the calculator. My next video, I'll pull that up and show you how to do it on there. And f prime of e, same type of thing. Just be able to find a tool that does this for you really nicely. I can just put e in there and use a number. So it's 1.698. And so we'll move on from there. It works well for cosecant and other functions. The thing about I want to say for the calculator is that there's a to do cosecant in here, you actually have to do 1 over sine. In essence, instead of that 1 over sine of theta, because there's no cosecant button on your calculator. And I'll show you how that works. All right, let's move on to the next piece here, which is the derivative means. We've done this before, but we just can't emphasize it enough. Don't get caught in a calculus class doing all these moves, which really is a bunch of algebra, and forgetting what a derivative does for you. It finds the slope of a tangent to a given place on the y function. The slope of the tangent line gives you the instantaneous rate of change at that moment, how fast the position is changing at that particular moment only. It's instantaneous. So when I say, hey, what's the slope at x equals 2 on a particular graph, you need to get y prime, because that's the equation, that the formula that gives you the slope. And 4 times 1/2 is 2, x to the third minus 1x, which means the derivative of negative x is negative 1. The derivative of 2 is 0. Now we'll put 2 into that function, and 2 cubed is 8. We'll do that next. So I get 2 times 8. Ooh, I just wrote 8. I meant to write 1. But 2 times 8 is 16, minus 1 is 15. That'll be the slope of the tangent line to this quartic function at x equals 2. Slope of the tangent line is what I'm talking about. Slope at a point, just different ways to phrase it. So it is the same thing. So it's still 15. But the difference is, write the equation of the line that goes there. And 15 is just the slope portion of it. So if I put this formula back in front of you, do you remember that this is y minus y1? It's the equation of a line. It's called the point slope form. It's when you have a point and a slope available to you. It's most convenient to use it. I just think it's the best one to use anytime. But what I get from this is the derivative gave me the slope alone, and that's it. If you want to know the x and y value, well, we have the x equals 2. they gave us. To get the y, I actually have to put 2 into the y function to get that out. And if I go through really quickly and I put 2 in here, let me write it in red so you can see I'm substituting 2. 2 goes in here, 2 goes in here. You want to do the math with me. 2 to the 4th is 16. Half of that is 8. 8 minus 2 is 6. Plus 2 again is 10. So, I'm sorry, 8 minus 2 is 8. So we have 8 minus 2 plus 2. So we ended up with just 8. I probably said something really funny there, but it is 8. So y2 is 8. So the equation of the line, all said and done, let's write it bold and red down below. The slope is one piece of the equation of the tangent line, because the equation of the tangent line is the whole thing. What would graph the tangent line, not just how steep it is, because the slope is just its slant or steepness. Okay, so there's the equation of the tangent line, just like that. And sometimes, like on WebAssign, it might ask for that, and it says solve for y, like write y equals the equation of the tangent line. Sometimes it doesn't. You can just write what I got circled down here below. Okay, so instantaneous rate of change, same kind of question. So it's the slope of the tangent line is a sense of how fast your position is changing at a time. You do need the first derivative to make that happen. So you get s prime of t first. So that'd be 2 times 4.9, that would be negative 9.6. I got this. 9.8. I guess that's 6, huh? T to the first plus 40. Writing and typing and all these things at once. Again, if you see something weird, let me know. So negative 9.8t plus 40, the derivative of 6 is 0, so I didn't write it. And then we're going to take and put in at 3 seconds, how fast is this thing moving? This is just the position, the location of it. S prime is giving us how fast it's moving at any given time, and the time we want is 3 seconds. I'm going to put that in, plus 40. And if you multiply all that with your calculator, negative 9.8 times 3 plus 40, I'm going to move on to good old Demoe can do that too. So negative 9.8 times 3 plus 40 gives me 10.6. Now here's the fun thing. If I would have put this in as s of t, and I can do that, I think it allows me to do t's, I think, equals, let's do negative 4.9. I want you to see how there are options to finding this. T squared. I wrote all these right, moving fast, and plus 40t. You guys can't see all the things I'm flipping around up here. Kind of fun to watch. There. So that's my s of t function that they gave us. If I said, hey, what's the slope of the tangent, and I said just use this, I'd do s prime of t, and I can actually put in that 3. Okay, it gives me 10.6, the same thing I got from, this is a numerical method. Here is my position function. S prime of 3 is the computer, Demoe, is actually taking and doing the derivative numerically. There's an algorithm behind it, and they're putting 3 into it. They're getting the slope of the tangent line to be 10.6, just what I got. The downside to Desmos is that it does not show you the derivative. It didn't show us negative 9.8t plus 40 is the derivative. It calculates the slope numerically without actually giving you that equation, which is invaluable. If your goal is just give me the slope of the tangent line or the rate of change at that spot, hey, awesome. I just need the number. This is the great way to go. But we did need the symbolic representation in ours. So it was 10.6. And it's measured in some kind of unit, so whatever it is, meters per second or whatever. If they were telling us this was in meters and this is in seconds, I don't think it gave us that, but that'd be a reasonable measure it, meters per second. We'll talk about normal line in a minute. Derivative rules, we already know those. Basically, it's derivative of a constant is 0. Here's the power rule. If you take the derivative of a constant times a variable, it's just that constant by itself. And then the sum or difference rule is when you're deriving things that are added together, you can just take the derivative of each separately. And it looks kind of fancy down below. Now, I will get to the normal piece of it. I'm checking my time frame. I think that might be a good place to wrap up in the final video in 3.1. And then I'll break into a couple examples. And the rest of the examples, I kind of circled some, and I'll forward this all to you guys that are the ones I'm going to tackle, that I hope to tackle. I'll do a few, but the rest I'll do during the office hours. If you feel like you can't get through these yourself, I'll send you the answer key to it, by the way. then this would be good things to ask about. I'll do these, send you the answer key no matter what, just fodder for questions as we get to tests and quizzes down the road. I hope that they use a lot of the similar types of questions you